Imagine you're standing at a critical juncture, maybe responsible for safety in a really complex system, like, say, a busy railway. The decisions you make, they could literally save lives. But here's the catch, right? The data you need to figure out the risk is, well, it's patchy, maybe incomplete, or sometimes it even seems to contradict itself. How do you make those vital safety calls then?
Yeah, that's a huge challenge in industries like railways, definitely. Traditional methods, things like probabilistic risk analysis or PRA, they work great when you have just tons of complete, accurate historical data. Hard numbers stretching back years.
Right, the ideal scenario.
Exactly. But the reality, it's often quite different. Detailed stats for every single potential failure. They often just don't exist, especially for those really rare but potentially catastrophic events. So what happens is analysts have to lean pretty heavily on expert knowledge, their accumulated experience, and just sound engineering judgment.
Makes sense. You use the people who know.
But the problem there is that expert input, it inherently carries a level of uncertainty, right? It's subjective, it's qualitative sometimes. And that makes it, well, kind of difficult to just plug neatly into those traditional mathematical models.
Okay, so we're talking about these situations where human intuition, experience, it's all super important, but it doesn't quite fit into a nice, clean spreadsheet. And that, I guess, is exactly where something really quite clever comes in. The fuzzy reasoning approach, or FRA, and the fuzzy analytical hierarchy process, fuzzy AHP.
That's it. And these aren't just theoretical ideas cooked up in a lab. They're actual tools, powerful ones, designed specifically to capture and process that crucial expert judgment, even when the information feels, a bit fuzzy or imprecise.
Okay, let's unpack this then. So for this deep dive, our mission is really to get under the hood of how FRA and fuzzy AHP work, how they tackle that uncertainty in railway safety, and ultimately how they help people make better, more informed decisions about risk. So first things first, what exactly is fuzzy logic? It sounds, well, a bit vague.
Yeah, it's a common first reaction. But fuzzy here doesn't mean imprecise in a sloppy sense. It really means dealing with degrees of truth.
Degrees of truth.
Think of it like this. In classic logic, everything's binary. True or false, on or off. A train is either moving or it isn't. Simple. But fuzzy sets, they let us handle the shades of gray. How much is a train moving slowly? Maybe it's like 30% slowly moving and 70% moderately moving. It allows for that continuous spectrum that often reflects reality better.
Ah, okay, so it's not just yes, no, it's how much.
Exactly. And to make this practical, we use a few key components. First up are fuzzy numbers. These are basically ways to represent those fuzzy sets mathematically. In engineering, you often see triangular or trapezoidal ones used. They're pretty intuitive and efficient to work with computationally. A trapezoidal one, for instance, it's defined by 4 numbers, and it kind of represents a range, but with the most likely area in the middle.
So instead of just saying between 3 and 7, it captures probably 5, but could be 3 to 7.
Precisely. It gets that human nuance of around this much. Then we have linguistic variables. Now, this is where it gets really interesting, I think. It lets us connect human language to the system.
How so?
Well, these are variables whose values are words or sentences, not just numbers. So an expert doesn't have to invent a precise failure frequency like 0.0053 events per year. They can use terms they actually think in, like remote or negligible or maybe highly unlikely, to describe different risk factors.
Ah, so you can directly use the expert's qualitative judgment.
Exactly. That intuition, which often comes out in words, can be systematically captured and processed. It's powerful. And finally, the core of it all is the fuzzy rule base. Think of this like the system's brain. It's a collection of if-then statements.
Like programming rules.
Sort of, but derived directly from expert knowledge. So a rule might sound like, if the failure frequency is described as remote, and the consequence severity is judged negligible, and the consequence probability is highly unlikely, then the overall risk level is low. It's like encoding their years of experience.
Okay, this is starting to make sense. You have fuzzy inputs, these rules process them. But what comes out? Is it still fuzzy? How do you get something actionable?
Great question. Yes, the initial output from applying rules is also a fuzzy set. It represents the combined implications of all the relevant rules. But you're right, a safety manager needs something clear. So the final step is called defuzzification. This process takes that fuzzy output set and converts it into a single, crisp numerical value.
A concrete number.
A concrete number, yeah. Often using a method like finding the center of area of the fuzzy set, that number is something managers can easily understand and act upon.
Okay, we've got the basics of fuzzy down. Let's dig into the first major technique you mentioned, the fuzzy reasoning approach. FRA. How does that help us quantify individual risks when the data is messy?
Right, so FRA is really designed for exactly that situation, modeling risks when your safety info is maybe incomplete, maybe even a bit redundant. Its main job is calculating the risk levels, the RLs, for individual hazardous events. And it does this by looking at three key things we've touched on: failure frequency, FF, consequence severity, CS, and consequence probability, CP.
Okay, FV Celsius CP.
Got it. So the process kicks off with inputting judgments. This can be historical data if you have it, sure. But often it's experts giving their best assessment, and they can provide this in different ways. Maybe a precise number like 50%, sometimes a range like between 60 and 70%, maybe a fuzzy number like severity is around 3 to 7, most likely 5, or those linguistic terms we talked about like failure frequency is average.
So it takes all these different kinds of input.
Yes, and that leads to the next crucial step: conversion to uniform format numbers, or UFNs. This is all about standardization. All those diverse judgments, the precise numbers, the ranges, the fuzzy numbers, the words like rare, they all get converted into a standard format, typically those trapezoidal fuzzy numbers we mentioned earlier.
Why trapezoidal specifically?
They're flexible. A precise number 5 can become 5555, a very narrow trapezoid. A range between 4 and 6 might become 4556. A linguistic term like rare gets mapped to a predefined fuzzy number, maybe 0.1, 0.2, 0.3, 0.4. This uniformity is key for the math that follows.
Okay, makes sense. Standardize everything first. What's next?
Aggregation of UFNs. If you have several experts providing input, you need to combine their judgments into one group assessment. And this isn't just simple averaging. You often use something called expert indices, or EIs. These basically weight each expert's input based on their competence or experience.
So more experienced people get more say.
Essentially, yes. Someone with, say, 10 years experience might have a higher EI, giving their judgment more weight in the final aggregated UFN than someone newer. It tries to reflect the value of that deeper expertise.
Right, so you get one combined fuzzy number for FF, one for CS, one for CP. Then what?
Then those aggregated UFNs go into the fuzzy inference process. This uses those if-then rules in the rule base. Common methods like the Mamdani approach are often used here. The system figures out which rules are relevant based on the input values we say those rules have non-zero fire strength. The conclusions from all those fired rules are then combined mathematically into a single fuzzy set representing the final risk level for that specific hazard.
And that brings us back to the last step you mentioned earlier.
Exactly. The final step for FRA is defuzzification. Taking that resulting fuzzy set for the risk level and turning it into that single, crisp, usable number using something like the center of area method. That gives you the RL for that one hazardous event.
Okay, so FRA gives us the risk level for individual hazards. But usually there are loads of different hazards in a system, right? How do we figure out which ones matter most, or how they combine to give an overall risk picture?
Ah, yes. That's where the second technique, the fuzzy analytical hierarchy process, or fuzzy AHP, comes into play. Its main purpose is to determine weight factors, WFs.
Weight factors.
Yeah, these basically represent the relative importance or contribution of each hazardous event, or maybe groups of hazards, within the bigger picture, within a whole hierarchy. It helps you see the forest for the trees, basically. It prevents information loss when you're looking at complex systems with multiple levels.
How does it figure out those weights?
The core idea is pairwise comparison. Experts compare just two things at a time, say hazard group A versus hazard group B. How much more important is A than B in terms of risk contribution? And again, they use linguistic terms for importance. They don't just pick a number. They might say hazard A has strong importance over hazard B.
And strong importance translates to a fuzzy number.
Exactly. Strong importance might map to a triangular fuzzy number like 456. Equal importance could be 1 then 100, weak importance 2, 3, 4 hours, absolute importance 8, 9, 9, and so on. It captures that relative judgment in a fuzzy way.
Okay, so similar process to FRA in some ways.
Similar in that these pairwise judgments are then converted to UFNs, aggregated if you have multiple experts, and then used to build what's called a comparison matrix. From that matrix, you can calculate the fuzzy weight factors, often using techniques like the geometric mean.
And then defuzzify again.
Yep. The fuzzy WFs are defuzzified into crisp numbers, and then they're normalized, which just means they're adjusted so they all add up to 1, or 100%. That gives you a clear percentage contribution for each hazard or hazard group.
So bringing it all together,
Yeah.
how do the FRA results and these fuzzy AHP weights connect?
That's the final synthesis. You take the individual risk levels you calculated using FRA for each specific hazard, then you use the weight factors from fuzzy AHP to combine them. This lets you calculate the overall risk levels at higher levels, like for sub-hazard groups, then full hazard groups, and ultimately for the entire railway system or operation you're assessing. It gives you that comprehensive, top-down view built from the detailed, fuzzy, bottom-up analysis.
This sounds powerful. Let's make it concrete. You mentioned a case study. Risk assessment for shunting at the Hammersmith Depot.
Yes, exactly. A real-world application. So for this study, they looked back at over 10 years of historical data from the Hammersmith Depot. From that review, they identified 7 main hazard groups, things like derailment hazard group, collision hazard group, electrocution hazard group, and so on. And each of those was broken down further into subgroups and specific events.
Okay, so how did the FRA analysis play out for some of those specific events?
Well, let's take one example. The risk of derailment, typical outcome. The safety team would input their best judgments using available data, but also their expert knowledge for its failure frequency, consequence severity, and consequence probability. These inputs get turned into UFNs, fed into the fuzzy inference engine. And for this specific case, it turned out only 2 rules in the rule base, rules R28 and R29 apparently, were significantly fired. They were the most relevant. After combining their outputs and defuzzifying, the final risk level for derailment, typical outcome, came out as 3.00. The system categorized this as possible risk, and it assigned a 100% belief to that assessment.
And other hazards had different results?
Oh, absolutely. For instance, electrocution, typical outcome, came out with a defuzzified RL of 6.00, which was categorized as substantial, again with 100% belief. So you get distinct risk profiles for each specific event.
Right, so FRA nails down the individual risks. Then what did the fuzzy AHP tell them about the bigger picture, the overall risk for shunting at Hammersmith?
The fuzzy AHP part involved those pairwise comparisons between the hazard groups to get the weight factors. When all that was combined with the individual FRA results, the overall risk level calculated for shunting operations at Hammersmith Depot was 2.99.
2.99, so that also fell into the possible risk category.
Exactly. Possible risk, again with 100% belief. The system was quite confident in this overall assessment.
Now, that possible category isn't just a label, is it? It implies action is needed. What did this analysis actually tell the safety managers they needed to do? How did it guide their response?
Precisely. Getting a possible overall risk meant risk reduction measures were necessary. The goal became getting the risk as low as reasonably practical, or ALRP. And the real value here wasn't just the overall 2.99 number, but the breakdown provided by the fuzzy AHP weight factors. It showed which hazard groups were driving that overall risk.
Okay, so where was the risk concentrated?
The analysis really highlighted the big 3. Derailment was the largest contributor, accounting for about 24% of the total risk. Collision was next at 21%, and electrocution followed closely at 19%.
Wow, so those 3 made up almost 2/3 of the risk.
Pretty much, yeah. Then you had the next tier. Train fire at 13%, train strikes person at 11%, slip strips at 7%, and falls from height contributing about 4%. This kind of detailed breakdown is gold for safety managers because it tells them exactly where to focus their limited resources for the biggest safety improvements.
Makes perfect sense. So what kinds of specific actions came out of this? For derailment, for example?
Well, looking deeper into the derailment risk, the analysis suggested that something like 92% of that risk was linked to human factors, things like overspeeding in the yard, incorrect routing by signalers, that sort of thing. So the recommended measures were very much focused there. Things like targeted staff training for shunters, signalers, drivers, implementing stricter speed limits within the depot, improving communication and liaison between different staff roles, and providing really clear, accessible reference manuals and procedures.
Very targeted interventions based on the root cause analysis. What about something like train fire?
Yeah, train fire was a smaller slice, about 13%, I think you said. Wait, no, 13% was fire, 10% was my mistake. Let me check that breakdown again. Yes, train fire, 13%.
Right.
The causes there were identified more as things like electrical arcing or mechanical failures. So the recommended controls were different, focused on rigorous, regular maintenance and inspection programs for both the trains themselves, the fleet, and the track infrastructure within the depot.
So the solutions directly matched the identified dominant causes for each major risk contributor.
Exactly. It leads to a much more efficient and effective risk management strategy.
Okay, so there you have it. A really fascinating look at how fuzzy logic, using these tools like fuzzy reasoning approach and fuzzy AHP, can genuinely transform risk assessment, especially in complex places like railways where data isn't always perfect. It's a method that seems to really embrace the nuances of human judgment and messy data rather than trying to ignore them.
I think that's the key takeaway. These methods move beyond simple yes-no, black-white answers. They embrace the shades of gray. And by doing that, they give decision makers a much richer, more comprehensive, and ultimately more actionable understanding of the risks they face. It's not just about ticking boxes or finding hazards. It's about truly understanding their relative importance and developing smart, targeted ways to manage them effectively.
So a final thought maybe for everyone listening. Think about other areas perhaps in your own work or life. Could be engineering, project management, even complex personal decisions. Where else is precise data hard to come by, but expert opinion or gut feeling is really crucial? How might this kind of fuzzy logic approach potentially change how risks are understood and managed in those areas? It's definitely something worth pondering. Keep exploring how these ideas might apply beyond just railways.